Now let us study the partitioning based algorithms. So in general, when we are looking at a partitioned algorithm, what we are talking about is that we want to divide the objects that we have, the database of n objects, into k clusters such that this function is minimized. So that is to say, every point P goes into a cluster I, which is represented by a representative point, and then we want to minimize this so that the every point belongs to a cluster which is close to it. And it is, say we are giving initially the number k, then we are trying to optimize using that criteria of k. See, if we are looking for really a global optimal, then the k may not be the most optimal. So we need to exhaustively create all possible number of clusters, and those number of clusters is going to be exponentially large. And then we are going to find out which is going to offer us the minimization of this function. And we have some heuristic methods for k-means and k-medoids, which we are going to see in a short while. So where we are saying is that we create the clusters for a given k in such a way that they are centered around a point which is a representative point. And to look at the steps involved in a k-means clustering, so here what we are doing is that we are looking at the algorithm. So this is very simple. So all we are doing is that we are arbitrarily selecting the k points, and it is possible that it is not going to be arbitrary based on, we may be able to do it on some consideration, but if we look purely at the k-means clustering, so it expects k points to be given initial points, and for each of the points data objects within the database, it is going to associate them with one of those k points, and then it is going to recompute a centroid for the new cluster based on the points that have been associated with each of the initially identified centroids. Thereby the cluster shape will be adjusting itself to its natural form. And the initial centroids, in general, they're supposed to be chosen randomly, but what happens is that if you choose a different set of centroids initially, you're likely to get a different set of clusters. And the centroid calculation is that what we do is we calculate the mean of all the points within the cluster for each of the attributes which have been transformed into some computable form. And we may use a Euclidean distance or a cosine similarity to measure the closeness of the points. And it converges generally for the similarity measures mentioned. And it is also likely that we stop when there is a changes within the clustering is minimized. And when it comes to the complexity of the algorithm, it is a linear with respect to each of these n, k, I, and then the d. So that is the number of iterations, number of attributes, then the k, which is the parameter given for the clustering, the number of clusters, and then the number of data objects or the points. So in that sense, this algorithm is a relatively efficient algorithm. So if we take these as the original points and we want to do a k-means clustering, so we may arrive at this looks like a natural division. So this is a optimal clustering that we arrived at, and we may also arrive at a suboptimal clustering, and we are going to see briefly how is it that we may end up with a suboptimal clustering in some situations. And having done the clustering, we are going to evaluate using the distance function, which we call as a sum of squared error. So that is, we look at the distance of the points, each of these points with a representative point, For example, it's a K clusters, and each point that belongs to the cluster I, we are taking the distance with the representative point for that cluster. So in case of a K-means, so the Mi is being represented by the mean of the points within the cluster. And let's look at what happens when we choose points along. Let's say we have chosen these 3 as the initial points, and then we may arrive at this form of clustering. So let's see, we start with this. So now we have the we have the initial centroids, and then we have associated all the points to the initial centroids. We can see the 3 colors to represent that. And now when we calculate the new centroids, they're going to shift. So we can see that the new centroids have shifted more towards the center of each one of these groups. And then we reassign each of these points, and then we are going to get a new set of clusters, the same 3 clusters but with a different set of points. And then we are going to recompute the centroid and then reassign. Then we are going to get points which are further moving towards the natural clustering. And then we can see that after 5 iterations, we have reached the natural clustering that is visible, clearly visible in this 2-dimensional space. And we may end up sometimes choosing a wrong set of initial centroids, or which lead us to a unreasonable clustering. Let's say we have chosen the centroids around these points which are shown here. Then what is going to happen is that after first iteration, the way they shift will be like this. We have assigned all the points to the centroids, and we can see there's still the 3 clusters, and then the points assigned to each one of those centroid. And then as we recalculate, we can see that the movement, at least in the bottom cluster, seems to be almost not there. So here we are ending up in a situation. So there is a fine adjustment within the top 2 clusters, but almost no adjustment with the bottom cluster. So after the 5th iteration and possible, so we have not been able to reach, and we are unlikely to reach further. So what we can see is that we could not get the natural clusters. So the point is that how can we be sure that we are going to get the points which are reasonable? So one way is to consider that there is a data set that is given to us. It is possible that there are k real clusters. As we have seen in the previous example, there were 3 real clusters. And if we had chosen the initial centroids all within their own real clusters, then we are certain of getting those clusters right. But what is the probability of that when we are arbitrarily choosing 3 points? They will belong to the real clusters. And mind you, this is not a problem we are solving for a much larger data set. Previously, we had seen an example where there are only 50 points, so it is much easier to find out the real clusters. But if you have got 1 billion points and then you want to find out the real clusters, it is just an impossible situation. So we need to depend on choosing how to choose the initial centroid so that still we can get reasonable set. As we can see here, when we do the probability calculation, for example, we are doing the clustering for 10 points, and then 10 is the clusters which we want to create. Then what we are ending up is that the probability of getting it right is very, very small. That each one of the points, the number of points is, it's not 10, it is some large number, but then the number of clusters that we want to do is 10. So in that case, the probability of getting the 10 points within those 10 distinct clusters is very, very small. So what it means is that sometimes they adjust themselves in a right way and sometimes they don't. Now let's look at another example. So let's see here, we have got 5 pairs of points. So when we want to create 10 clusters, it makes sense if we get the 10 clusters. There are 10 natural clusters, but they are organized in such a way that they belong to 5 pairs. And if we had chosen the points such that each at least one or at least 2 points are there in each pair, then we are assured of getting the natural clusters. But let us say we don't do that and we choose 1 point from one pair and more than 2 points in one pair. As it happens, finally we are not going to find the natural clusters here. Though the 10 is the right number, we could not do the clustering in a correct form because the initial centroids that we have chosen were not good. So how do we solve the problem of getting the initial centroids right? One is that we may run with many possible combinations, but for a large K, the probability is not in our favor. In fact, we may have to run million runs before we get one correct possibility, because once with the K is large, as we have seen, the number of possibilities and the probability of getting it right is going to be smaller and smaller. So other approach is that instead of using pure K-means approach, we also use another form of approach of clustering. Thereby we get an idea of the set of clusters that we have, and then we try to find the initial centroids from the idea of the clusters that we have got using another approach. So thereby we are going to get things better. Or the other thing is that other way we can do is to do some pre-processing. After creating the K clusters, we analyze those clusters and think in terms of reorganizing those clusters. So the pre-processing that we can do for any cluster analysis algorithm is to do a normalization of the data. And since the K-means algorithm is susceptible to the outliers, if there is an outlier present which is very distant from the other data, so that is going to significantly influence the shape of the clusters that we create. So we need to eliminate the outliers, and then the post-processing is that we look at the clusters that we have created and identify the some which are loose clusters which have got a very high squared error, and then we look at some small clusters which may be getting created because of the existence of the outliers. Outliers is, for example, we have some points which are close to each other and there is one point which is far off. So in such case we will end up creating a cluster for this, though it should have been eliminated as a noise. And we may merge some of the clusters which are very close and which lead to a low squared error, and thereby we can improve the clustering. And the variations that exist with the K-means, largely they come from the way we select the initial K-means, and also with the way we use the dissimilarity calculation, and the way we calculate the mean of each of the clusters, so that we keep moving the cluster mean and then recalculating the clusters. And also the K-means algorithm has a challenge with respect to categorical data. So in this case, we may go for a mode as the approach, because for a categorical data, finding out a mean is a real challenge. For example, we have done a customer segmentation, and in one cluster we realized that there are 100 customers, and out of them 50 are let's say lawyers, and 20 are teachers, and 30 are doctors. So in this situation, finding a mean is just not possible. So what we do is we may consider that since the largest number are belong to particular profession, so we may use the mode and simply proceed with that. So in such situations, we need to think in terms of how to create a dissimilarity measure so that we will be able to find the distance more accurately. And the K-means has a problem when we get a data with wide-ranging density. That is to say, at some places the density is low and at some places density is high. And if it has to find clusters which are of widely varying sizes, then also it is going to create some problem, and it can't handle the outliers well. So if we are looking at the original points where we are seeing 3 natural clusters, The k-means may offer us the clusters of this kind which are not representing the natural clusters for the simple reason of the way we have chosen the points and we have done the calculations. And when there is a wide ranging density, then we are going to get a different form of a k-means clusters. So as you can see here, it does not recognize this density and natural clustering here. So it is going to create a cluster of this together, because that is going to give it a better mean and the squared error. And the k-means cluster, since it always goes by the distance measure, it has a challenge with finding the contiguity. For example, here we see two natural clusters based on the contiguity, but when we are doing a distance measure, we clearly see that the 0.1 and 0.2 will have a very low distance compared to 0.3, 0.4, which belong to the same natural cluster. 0.3, 0.4 belong to the same natural cluster, but they have a very large distance. So in this case, the k-means algorithm is going to be confused, so it is going to create clustering of this form. So one way we can overcome is that we increase the number for k. So that is, instead of having a smaller number, we have a larger number. So we are creating many clusters, and then we may find some of them which can be joined together based on some criteria. And similarly here, we are creating many clusters, and at this point we may be able to join them based on some criteria and then get this natural cluster. And here again, we may find some ways to join and then get the natural clusters. And to just retrospect on k-means, so one significant characteristic is that it's a very significant, efficient algorithm, and it is very linear with respect to the number of objects, the number of clusters, and the number of iterations. And so it is efficient. And compared to some other algorithms which are based on partitioning, it is even more efficient than compared to that. In this case, we expect the objects to be present in a n-dimensional contiguous space, because we are not recognizing the natural breaks or the discontinuity between them, and we are measuring the distances uniformly, as we have seen in some examples. We had a challenge with finding the natural cluster because we considered it as a contiguous space. And it has a challenge with respect to using the categorical data. So we need to depend on k modes, because the mean cannot be calculated in such situation. And we have a alternative which looks similar to k-means, which is referred as k-medoids. Medoid is a point within the cluster which can be used as a representative. Mean is a point which is most likely not a part of the cluster. So if we have got, let's say we have a cluster with 3 points, and the mean will be here. This will be the mean. So because that is representing the sum weighted average among all of them. But if we are looking for same points and we want to find out a medoid, then we need to look at which one is better. So maybe that we'll find this is a better medoid than the other two based on some criteria, so on. So the thing is, the medoid is actual data point, and k-means does not work well when we want to create a non-convex shapes. So if we are looking at a partitioning around the medoids, so there is a popular algorithm PAM. So here what we do is that instead of arbitrarily choosing some centroids, we are choosing points, k points within the data. And then we are measuring the distance, and then we are creating the clusters around these k medoids. And then we are going to shift and find out if there is an alternative point which can be replaced with a non-medoid, can be converted into a medoid, and then proceed with the further clustering. So this approach works effectively when the data set is very small. The simple problem here is that whenever you create one cluster which has got, let's say, 1, 2, 3, 4, 5, 6 points, and we currently have this as the medoid, then we need to find with every other possible point, if we change this to 0.1, is this going to be a better medoid than this 0.0, or is this point going to be better, or is this point? So that means for finding a new medoid, we need to do a complex calculation. So that is going to increase the order by the number of data points that we have in our space, which we are trying to cluster. So because of that, this is significantly increasing the computational complexity when we have a large data sets.